and acceleration in simple harmonic motion. Consider a particle p with v equals to linear velocity of particle, omega equals to angular velocity of the particle, a equals to radius of the particle, and p dash is the projection of particle p. Now let's understand the particle's displacement in simple harmonic motion. You can see a particle moving along a wave. The displacement x, t of particle executing SHM with phase angle phi equals to 0. This figure is a plot of equation Vt equals to minus omega a sine omega t plus phi with phi equals to 0. Now let's understand the velocity Vt of particle in a simple harmonic motion. Here in the graph, plus omega a equals to velocity amplitude mu m. In this figure, the velocity of oscillating particle varies between the limit plus minus mu m equals to plus minus omega a. Now let's understand the acceleration at of a particle in a simple harmonic motion. You can see a graph a versus t. Now let's compare the displacement and velocity of the particle executing simple harmonic motion. You can see the three graphs of displacement, velocity, with velocity lags behind the displacement by a phase angle of pi by 2. Now let's compare the displacement and acceleration of a particle executing simple harmonic motion. You can see two graphs of displacement and acceleration. When displacement is 0, acceleration is also 0. Phasors. A sine wave can be represented by a rotating vector called as phasor. The magnitude of phasor is equal to magnitude of the sine wave, and the y component of phasor matches with y value of sine wave at every instant of time. We have two phasors with the same angular frequency omega. The green one Eg sin omega t and the blue one Eb sin omega t plus phi. The blue one leads the green one by phase angle phi. At every instant in time, the y component of each phasor matches the y value of the respective sine wave. As we discussed earlier, that if a particle p is moving on a circle, then v equals to velocity linear of the particle, omega equals to angular velocity of particle, a equals to radius of particle, linear velocity v equals to a omega. The velocity vector v of the projection of particle at time t is vt equals to dx by dt. Thus x equals to a cos omega t plus phi. Shows the simple harmonic motion along x-axis. Thus vt equals to d of a cos omega t plus phi upon dt equals to dA cos omega t plus phi by dt into d omega t plus phi by dt. Thus we get the equation Vt equals to minus a omega sine omega t plus phi. Also, angular acceleration at time t is given as alpha t equals to dvt by dt. Substituting value of Vt, we get alpha t equals to d of minus a omega sine omega t plus phi by dt. On solving, we get alpha t equals to minus a omega d sine omega t plus phi by dt dot d omega t plus phi by dt. Hence, alpha t equals to minus a omega square cos omega t plus phi. For the velocity vector v, xt equals to a cos omega t plus phi. Thus, alpha t equals to minus a square omega xt.